Hello, everyone, and welcome to Chapter 3. It's time for things that get a little chaotic with entropy. So, up until now, we've been focusing a lot on enthalpy and internal energy, which is essentially a measure of where the energy is inside of a system and relatively how stable the system is. But what it's not really telling us is anything about what if I have two states, which one is going to be more favorable? All I can say is which ones are possible, simply based on the first law, knowing that energy has to be conserved. But what I'm not getting any information about is where the energy wants to be and how the systems progress. So if I start with a compressed system, I know I can describe exactly how it would look in an expanded state, but I have no information about whether the compressed or expanded state are more favorable. So, for that, we need to build up a measure of where energy wants to be. And it turns out that we actually do have a pretty good intuitive understanding of this idea of favorability. A good example is, say, imagine I've got two pots of water, one at a high temperature and one that's at a low temperature. If I go ahead and put them together, which direction is the energy going to tend to flow? In general, it's going to go from hot to cold. So we already know that a high temperature means a high internal energy, and a low temperature means a low internal energy. And so what we can do is build upon this idea that energy tends to want to disperse. So it tends to want to go from high to low. And this is one of the basic uh, fundamentals of thermodynamics. And it turns out we can really phrase this idea of hot to cold as its own law of thermodynamics, which is the second law. And it turns out that it has several descriptions, the simplest of which is heat does not flow spontaneously from a cool body to a hot body. So essentially, I'm never going to see energy go from cold to hot, indicating that I'm going to likely see energy going from hot to cold, but again, not necessarily. And we can also reframe this in the way of essentially the chemical engineers or the early thermodynamics guys who are focused on energy and specifically things I can do with energy. So they love their engines, as we've seen with pistons. And so what we can do is take this idea of a piston and turn it into an engine by essentially letting energy flow out as heat from a hot source, such as, say, a fire, and then trying to capture that energy as work. But the second law says that I can't take all of this energy and turn it all into work. Some of it's going to have to flow out as heat to essentially a cold source, because we already know energy is going to want to go from hot to cold. And so I can capture some of this energy as usable work, but I can never capture all of it. And we can think about this in the same way that we would, say, a dam. I can have high water with lots of energy, and I can have essentially the stream flowing away from it with low energy. But I can't take all of the energy from the water in my reservoir and turn it all into work into a turbine. I have to let some of that water and its corresponding energy flow through. And this idea that we can't completely capture energy from any source is an important fundamental idea of thermodynamics. Thus, the reason it's the second law. The only one higher up is, well, conservation of energy. However, it turns out we can also express the second law in terms of a state function. Because again, we love to be able to describe as many of our properties in terms of measurable quantities as we can. And so what we do is we describe the spontaneity in terms of entropy as our new state function. And we can essentially define entropy in a different formulation of the second law, simply that the entropy of an isolated system is going to increase in the course of any spontaneous change. And this is pretty much our definition, that in order for something to occur, the entropy of the isolated system has to increase. So I need some sort of state function that's going to that's only going to increase when whenever I have something that happens naturally. And if I have something that's an unfavorable reaction, this total entropy should be negative. And thus, we have a simple metric of saying whether something is possible. A reaction or any sort of process, an expansion, a compression, is going to be possible if my total entropy is positive, and it's going to be unfavorable if it's negative. So any spontaneous process is going to increase the entropy of the universe because the universe is pretty much my biggest isolated system. It's the isolated system that encapsulates all. However, it turns out that most of the time, I don't care so much about the entropy of the universe. I care about the entropy of the individual process or reaction that I'm examining. So what we do is we tend to split the entropy of the universe up into two parts, into the system that I'm studying and the surroundings, which is everything else that I don't care about. And so it turns out that while the entropy of the universe always has to increase, I can see some local decrease in entropy, which means that I can make things slightly more organized on a small scale as long as I make things much messier in somebody else's yard. And so this is one of the major driving features of trying to determine what can happen in chemistry, is this idea of trying to balance what can happen in the system I'm looking at versus what disorder am I causing in the surroundings. So what we're going to do next time is to look a little bit more at this idea of entropy and what is it really telling me. From the colloquial description, entropy is usually going to be considered a measure of disorder, but it gets a little bit messier if we look at it on the fine scale. So next time, we're going to be looking at a very small scale of entropy and seeing what pops out. Till then, take care.